Okay, so then the following are equivalent for the group G, which is, Kimmel problem has a positive solution for G. G is a group of H. G is contained in a bigger group. Okay? Okay. Well, okay, so it's to verify that Kimmel problem has a positive solution. What you have to do is calculate. These are not the partial augmentation anymore because we are calculating the coefficients, the sum of the coefficients on the elements of a given order. They have to be non-negative. And this is equivalent to, well, this statement, but with a very concrete group. There is a natural way to embed one group in a permutation group, which is the natural way, which is using the regular representation. So we consider the elements of G as permutation of G by multiplication. Okay? So we consider always G contained in permutations of G, the symmetric group on G, in the standard way. Okay? So the third one is this statement for that concrete group. Okay, so you don't, I mean, the Kimmel problem can be, I mean, this H in the Kimmel problem can be said explicitly who. Okay, you don't have to look to fish in a big ocean of groups. You have to consider one concrete group. Okay, the proof is written, but I will give you the basic idea. The basic idea is that when you consider a group element now as a permutation, okay, so which is multiplication by G, the cyclic structure of this permutation is a product of cycles all with the same cardinality. Okay, the order of the element. Okay, all these elements belong to the same conjugacy class here because of the class. I mean the classification. How are the class? The conjugacy classes in the permutation group. Okay, and so. Of course, only the partial augmentations on the classes containing an element in the group are non-zero because your original unit has coefficients in G. But all the classes in all the classes containing one group element, okay, fuse in a unique conjugacy class in the permutation group because all of them, I mean, with a group element with the same order, all of them has the same cycle structure. So they go to a conjugacy class. So the different conjugacy classes of elements of the same order fuse here in a unique conjugacy class. Okay? And what you have to check for your original group element to belong, to be rationally conjugate to an element here, well, not to an element here, to an element in the group, now the group is the big group, okay, is this condition. But now the conjugacy classes, remember, all the ones with the same order are in the same place, okay? And this is the way to check that this condition here is satisfied, because these are all the elements with the same order are in the same conjugacy class. Okay, so you are only summing one, elements in one class. And of course, this is equivalent to these partial augmentations, not partial, but now partial augmentation in the big group are 0 except for 1. Because, I mean, the total augmentation is 1. If you are summing non-negative integers, one is 1 and the others are 0. Okay? Well, this is the basic idea, okay? And correct. Right, no, but the point is that this condition, when you consider this statement in the big group, it exactly takes this format. Of course, not exactly this format, but this format. Okay, where H is the big group. But it's clear that this is the same as this, because outside G, everything is 0. Okay, so this is the basic idea. But what I'm going to explain in the rest of my talk is what is called the help method. Okay, this is a method to verify if this holds. Okay, for all the possible units. Okay, helps comes. The name comes from Luther and Percy. Who introduced it to prove the Sachsen-Hauss conjecture for the alternating group on 5 symbols. And Hertweg, who extend the method by using, well, Luther and Percy used ordinary characters, and Hertweg proved that you can also use Brouwer characters, and then the method with the Brouwer characters plus ordinary characters was more powerful than if you only use ordinary characters. This method has been implemented by Leo Margolis and Andreas Mariana, so we have a GAP software which implements the method. And they, well, the package needs to be compiled and its installation is not that obvious. So those who are interested, please approach to one of them, to Andreas or Leo, also to me, but I won't be able. I mean, they did it for me yesterday, and they can compile it in your computer. So, but don't try to do it yourself because it will be very, very complicated. Leo? It doesn't work in Windows. Only for Linux and for Mac, okay? But in Windows, you cannot use it. Say sorry. Me too. Anyway, so I am going to explain what is this about, and maybe in the tutorials or in the GAP tutorial, they will show you how it works and okay. Okay, remember that what we want, I mean, maybe this should come to the end, but at least to have it in mind, what is the goal is to prove that for every torsion unit is rationally conjugate to a group element, okay, So, or equivalently, that these numbers, all these numbers, are non-negative when you start with a torsion unit, divisor of the order, and a conjugacy class. So you have to prove that a certain list of integers is non-negative. Okay? And the method, what the method does is a list of restrictions of this list of numbers. Okay? So in terms of some, not necessarily, well, linear inequations. Okay? Diophantine linear inequations. You look for integers which satisfy these linear inequations, and if you prove that all of them are non-negative, you finish. Of course, you have to do it first. I mean, the method goes order by order. So you fix one integer, and you apply the method for that integer. Okay? Then you should say, okay, but how many integers? Okay, which integers? Well, you know that the order of every torsion unit, as we prove it here, divides the order of the group. So it's an infinite set of integers. Even you can prove that it's a divisor not only of the order of the group, of the exponent of the group. This is a consequence of one of the problems, the Cohn-Livingstone theorem. So you only have to consider integers dividing the exponent of the group. Okay, and for every of these integers, you have to prove that all the possible partial augmentations, I mean, the list, because it's not one partial list, this list of numbers, okay, with a n fixed, are non-negative. Okay, and now I will show you how this works. And prove it at the same time that I show you. Well, we start with a, this is my notation for a fixed, primitive, complex, primitive, nth root of unit. Okay, and I take all the primitive root of unit, all the nth root of unities, and I put them all together in a van der Monde determinant. Okay? Okay, so we have this van der Monde determinant, and we take the complex conjugation. So we apply complex conjugation everywhere, which is, of course, the van der Monde determinant of the, actually here you can put the complex of this one is the inverse. Okay? And now you multiply the two matrices. And this is exactly n times the identity. Okay, so this is, you do it, and it's a triviality. Okay? Actually, yeah. So which means that this matrix is invertible, and the inverse is exactly the complex conjugate divided by n. Okay? And now we take any matrix, any invertible matrix, and by a matrix over the complex, but assume that it has finite order, so that u to the n is 1 for some integer n, not necessarily order n, this is not important. Well, and we diagonalize u, so u is conjugate to a diagonal matrix, and in the diagonal you only have roots of unity, nth root of unity. So these guys. Okay, each of them appears a certain number of times. So I am going to use the following notation. Which notation? I forgot it. Mu 0, mu 1, 2, meaning that these mu i's are the multiplicities. So 1 appears in the diagonal form, mu 0 times, theta n appears mu 1 times, etc. Okay, so we know exactly these mu's represents the repetitions. Okay? Of course, u to the j is conjugate now to the diagonal. Well, this j times mu 2, sorry, yeah, j mu 1 times, etc. Okay, of course, now we may have repetitions, so these guys are not the multiplicities, but okay, the notation is clear. So that we repeat the numbers. Okay, so then it's clear that the trace, the trace of u to the j is mu 0 plus mu 1 theta to the j, mu 2 theta n to the 2j, etc. Okay? So I can write this in the following format. If I calculate all the traces of the different powers, okay, so these numbers are this number with j equals 0, etc., and this is certainly the result of multiplying the van der Monde matrix by the different multiplicities. Okay? And so, because this is invertible, the multiplicities are 1 over n times v. This is the inverse of v, and now I write the traces of the matrix. Okay? So this gives you a formula for the multiplicities. Something is wrong? Yeah. So the multiplicity of theta n to the j is exactly that. Okay, so these are non-negative integers, and so we have that. And now I'm going to use the Sam-Galois theory. The Galois group of this extension is formed by maps where this j goes from, where this j is coprime with n, and this sigma j is simply rising a to the j. Okay? And well, if I start with any j, okay, and I take the greatest common divisor with n, now j over n is co-prime with d over n. Okay, so sigma j over n is an element in the Galois group of Q theta d. Okay, over Q, but this is right? No, something is wrong here, of course. This is n, something is j over d is co-prime with n over d. Okay, and so g over d is in the Galois group of this guy. Okay, so if I classified here the j's with the same greatest common divisor, so I can first run on the divisors of n and then run on the j's from 0 to n minus 1, whose greatest common divisor is exactly d, okay? Now this theta n to the j is here, okay? And to the I, the I. Therefore, no, this guy, and therefore also all this guy, okay? Yeah, can do it. Sorry? Well, that was I, correct, this is I. Right, correct. Then it's to the I. Okay. Well. Correct, I can write this as theta n d I over d, because I write this I as d times I over d, but theta n to the d is exactly theta n over d. Okay? So this is exactly the result of applying j divided by d to this theta n to the I. Okay? Okay, I did something strange, but anyway, so in the end, you can rewrite this as in that format. Okay? Okay, now, so we have this concrete formula to calculate the multiplicities. These are none. And now I start with my torsion unit, torsion element of order n. And I take a representation of G. And I calculate rho of U. So this is a matrix such that U to the n is the identity. Okay? So I can apply all this to this matrix. Okay? But, so let's denote mu theta n to the I u. Well, now let me leave this free for the multiplicity of this matrix, of theta n to the I as an eigenvalue of this matrix. And this formula tells me that this is well, here I made a mistake. This should be D. Okay. Well, the trace of this matrix, because this matrix is the image of U, is exactly the character of U to the D. So this does not depend on the representation, only depends on the character. So it doesn't matter which representation you take. So this is the multiplicity of the image of U by any representation affording this character, the multiplicity of this unit in this image. Okay. I have this formula. Well, this is a group ring element. So I can write it as a group ring element and apply the character here, but the character is linear and a class function. Okay? So you can just, I mean, when you write this element as a linear combination of group elements and you apply the character, what you obtain is this, but in the same conjugacy class, this is constant. So assume that I denote this anytime that C is a conjugacy class containing G. So I can rewrite this running on the conjugacy classes, okay, and this is same in the same conjugacy class, but now I have to add the coefficients of the elements in the same conjugacy class, and this is exactly the partial augmentation. Okay, so I can use this here, and this is, well, I mean, these guys are integers. So when I plug this here, I can pull out the integers. So in the end, I obtain the following. I am cheating a little bit because it's not clear that I can apply, I mean, that this element belongs to this field, but with some theory you can prove that it belongs. Or the coefficient of this guy is 0. So it works. Anyway. Okay. And these are the elements that we want to show that there are integers. Non-negative, I'm sorry. These are integers. I want to show that these are non-negative. So we have here a linear combination of these elements. These are integers because these are algebraic integers, and therefore a trace of an algebraic integer is an integer. So we have a linear combination, not exactly with integral coefficient, because here we are divided by n. Well, but we can put the n to the other side. And what is this? This is a non-negative integer. So this is a non-negative integer. And these are the conditions. Okay? And this is the base of the help method. The numbers that we want to show that are non-negative integers satisfies this property. Okay? So I can do the following. I can replace this by, say, some variables. These are now unknowns. Okay, so I have there a system of Diophantine linear inequation. Diophantine because what I want to, the solution that I'm interested in are integers. Okay, I can solve all this equation because there is one equation for each character and each I. So I have a lot of conditions, okay, for a given n, and I solve it. A linear optimization problem, okay, and I can find all the solutions. And there is a gap software, which is what help uses, who solves the linear inequalities. Okay? If I look for all the solutions, and all the solutions are non-negative, right, I'm happy. Because all the possible partial augmentation or torsion units are solutions, and if all of the solutions are non-negative, all are non-negative, and then this, in that case, I said that the help method, well, the Luther-Parsi method satisfies, proves the Sassenhaus conjecture for units of order n. Now I run on all the possible n's, and the possible n's are finally many, so the different divisor of the exponent of the group, and if this whole, this works for all the possible n's, I'm done. The Sassenhaus conjecture holds. Okay, Luther and Parsi use the method this way to prove the Sassenhaus conjecture for A5. Okay, so okay, they solve the equations and okay. Hertweg, as I told you, extended that it's exactly the same equations. The same property, the same linear inequality. These are not only linear inequalities, it's also, this has to be an integer. Okay, because you are divided by n here. So basically I say that this has to divide n and non-negative. Okay, using Brouwer characters. Okay, so it's not a triviality, you have to prove several things, but and to make sure that it is applicable, the method, and for some cases where the Luther-Parsi method, so where you only use ordinary characters, the method doesn't work, well, with using also Brouwer characters, they were able to prove that. You can check the Sassenhaus conjecture. For example, for A6, the alternating group on 6th letter, the Luther-Parsi method does not work for orders 4, 6, and Luther-Parsi without Brouwer character 4, 5, and 6, I think. I don't remember the numbers. But at least for 3 of them. But if you use the Brouwer characters, you can rule out 2 of these orders, and only 6 is left. So this tells us that the help method not always gives you the solution, because which means that, okay, maybe there are solutions of these equations which have some values which are negative, so then you have, in that case, this doesn't mean that the Sassenhaus conjecture don't work, it's not satisfied, it's not that, because you still don't have a unit. You simply say properties of the partial augmentations. And then you need to show that there is a unit with this partial augmentation, and if you prove that there is not such a unit with that partial augmentation, then also Sassenhaus conjecture is okay. Okay? You can also use it for some of the other problems. For example, remember the spectrum problem. Okay? The spectrum problem asks if the spectrum of the units of augmentation 1 is the same as the spectrum of the group. Of course, every element in the spectrum of the group, so every element, every number which is the order of an element in the group is the order of an element in the group of units. Okay? Is the other inclusion that you have to show. So you have to show that if in your group there is not units of a certain order n, there are no torsion units of augmentation 1 with the same order. Okay? But then you say, okay, let's consider the solutions of that equation for n. That's the way. If you prove that there is no any solution, there are no units of that order. Okay? Okay? And this has been used also in that way. Okay? Okay. Basically, I said what I wanted to say, but it's probably good if we do something for the. We maybe can use this time to do what we were not able to do in the tutorials, Andreas, and to finish that problem. Okay, can you come and do it? Okay, maybe it's in that way we use this time to, for example, to prove the Sachs-Hauss conjecture for S3, but it will be okay if we do it both ways, the way the problem was planned and then using the help method. Okay, please. Yeah, sure. It's open. Okay, very good, very good, very good. Yeah, I'm glad to ask you because, well, first of all, the counterexample of the Sachs-Hauss conjecture could be a counterexample to the kimmel problem, but it's not, because we know that the units which are counterexample satisfy the kimmel. So there is some result which ensures that a certain units satisfy the kimmel problem, and that particular case satisfies this. Second, Andreas, Mariano, Serrano, and Kimmel prove it for supersolvable groups. Kimmel problem is proved for supersolvable groups, but it's open. It's meta-abelian, but which implies it's solvable, but still this is not counterexample for the Kimmel problem. But as far as I know, it's open for solvable groups. Okay. Observe that the positive solution for the Kimmel problem implies a positive solution for the spectrum problem. And of course, this implies a positive solution for the prime graph question. Okay? And this we know for solvable, this we know for supersolvable, but we don't, the Kimmel problem we don't, is open for solvable. Well, it's open for a meta-abelian even. Okay. Omnipotent by abelian. Okay, good, good. You prove for nilpotent by abelian, so for meta-abelian. Okay, very good. I didn't know that, or maybe I knew it and I forgot it. I'm sorry. But as far as I know, for solvable in general is open. Okay. Open. Abelian by supersolvable, I don't know. By supersolvable, yeah. Right, right, right. Oh, okay, whatever you like. Thank you.